Hallo allemaal.
I think we are on air.
We are on air.
So, good morning, everybody. Good morning here at the technology stage on an early Wednesday morning. And I'm very happy to see you all here. And we are going to talk about carbon, carbon capturing, carbon technology, carbon neutral or even negative greenhouse technology. And we have a very good panel with us this morning. My name is Erik Egberts. I'm active in the horticulture already for more than 25 years. Seen most of the companies in the greenhouse technology supply industry over the last 5 years, at the time that I was the CEO of Dutch Greenhouse Delta. I'm very happy to introduce you to the panel for today, a high-level panel. We have roughly 45-50 minutes to go. If you have any questions, please bring it forward, because I think we all like to have a very interactive discussion. We have 3 short presentations, around 8 to 10 minutes, and then we kick off with the panel discussion. We kick off with Delphi, with Stijn, senior researcher at Delphi. Then we have Brigitte from TNO. And at the last, it is Wouter Kuiper from Cubo Greenhouses. So first, I give the floor to you, Stijn, for your 8 to 10 minutes.
I will try and do my best to stick to those time limits. Good morning, everyone. Welcome. Very excited to be here. My name is Stijn Jochems. I work as a researcher at Delphi Improvement Center. I also gave a presentation yesterday about LED lighting. For the ones who don't know me or don't know Delphi, Delphi is a company that develops and implements knowledge. My role specifically is to coordinate research projects that have to do with energy efficiency, LED lights, and also more recently, carbon dioxide efficient strategies. We have multiple facilities where we grow tons of different crops, and we really try and bridge the gap between fundamental research and practical applications. So we work together with a lot of suppliers, lots of breeders, lots of growers, and we really try and focus on the challenges that growers face on a daily basis. So a bit of background, long-term goal for the Netherlands is to grow climate neutral in 2040. A sub-goal is to almost halve the emissions of carbon dioxide by 2030, which can be done mainly by using less gas in a greenhouse. In the Netherlands specifically, most greenhouses use gas in their CHP, combined heat power, which is basically a motor, an engine, which burns gas. Then you get electricity used in the greenhouse for lights to grow plants in winter. Carbon dioxide, of course, a vital part of photosynthesis. Without it, we get reduced yields. And heating, to make sure that the greenhouse is the right temperature. In a fossil-free horticulture, though, we will not be using gas, which means that we will not be using the CHP in the same way as we always have done, which really causes an issue because we need to get CO2 or carbon dioxide from an external source. Those external sources, I put a couple of examples here. OCAP, so basically a network from the harbor of Rotterdam to the cluster of horticulture in the Netherlands. Liquid carbon dioxide or direct air capture can all be different sources. Doesn't matter the source. What we think will happen is definitely carbon dioxide will get more expensive. And if you think of fertilization, it would be very crazy to think that you use a fertilizer that you only use for about 10% of its efficiency. So 90% of that fertilizer is basically not used. And that is actually what happens here. I will also touch on about it later, but if carbon dioxide is really expensive and we're not using it efficiently, we have to think of different ways to use it more efficiently. So CO2 is lost because temperature increases, the sun heats up the greenhouse, humidity rises. We don't want to get too humid. We don't want any fungus problems. We don't want any reduced yields. So what we do is we open up the windows. We lose a lot of carbon dioxide. That is why a lot of CO2 is then lost, especially in summer, through open windows. Ideally, we would want to have about 800 ppms. You can see in the left graph, there's a curve. Above the 800 ppm, it costs significantly more CO2 to reach higher levels, and it doesn't really get you an extra return. On the right graph, you can see with the y-axis, the micromoles of intensity. So the more light you have, ideally, you would want to have more CO2 as well. And there's also a temperature effect. So the blue line says 27.5 degrees, so it's very warm, which also makes sense if you have a lot of sunlight, you can accept higher temperatures in a greenhouse to use the CO2 more efficiently. If you have lots of light, light is not the limiting factor, carbon dioxide is the limiting factor, so you would instead much rather keep the CO2 inside, keep the heat inside, and have an overall higher photosynthesis. This is also what we focus on in our trials. So this is an example of the tomato trial. On the y-axis is the weeks of the duration of the trial. The green line is the CO2 content, and you can see that the CO2 content normally is kept around 800 ppm, because that's the sweet spot of where we want to be. And you can see that the red line, the dosed carbon dioxide per week, is really low in the first couple of weeks, but as soon as the summer hits, we dose a lot more CO2, and the concentration of the greenhouse actually goes down. Yeah. To explain that, I also put in an example of the pepper trial, which is just a day in June, more recently. And you can also see the blue line is the concentration of CO2 in the greenhouse. It goes down during the day when the windows, the yellow and green line, are open. The red line, though, means that we are still dosing CO2. We're putting lots of carbon dioxide in, but the straight horizontal red line is the outside concentration. What we're actually doing is we're putting lots of carbon dioxide into the greenhouse, and most of it is lost. And that's where what I mentioned with the 90%, the 10% efficiency during those days, we're just losing lots of carbon dioxide, which right now maybe isn't as big of a deal, but as carbon dioxide becomes more and more expensive, it definitely will be a focus point. That's where a lot of models also come in. So Wageningen, for example, have made lots of models. Using the models, we're able to say, when windows are open 20% or more, we're losing like 90% of it. In summer, CO2 losses, about 70 to 90%, can outweigh production differences. So if you're putting lots of CO2 in, you're losing most of it, and you're not really getting anything out of it. Some models say, just stop dosing CO2, dose lots less, because you're not really having that low of a yield increase, or big of a yield increase. And also preferably increase dosing in the morning when it's relatively less warm, less sunny, to use the days where, or the time of the day where the windows aren't as open as much, and you use your CO2 a lot better. A challenge is bringing those models to the actual practical situation. Like, we can think of, okay, so let's dose CO2 in the morning because that must be better. We're having the windows open lots less. But sometimes we want to have a colder temperature in the morning in certain crops, for example. That is a challenge. The other one is finding the optimal CO2 source for a specific situation, specific location in the world, but also specific cultivation. Solutions may be different, might not be a one solution fits all. And there's also the big question about how expensive actually CO2 will be. And keeping that into account, prices of direct air capture. Direct air capture is, I'm sure the other panel members will discuss about it more. You take CO2 from outside, put it inside the greenhouse. That costs quite a lot of energy, but it might be worth it if you can that way get some carbon dioxide inside the greenhouse. Conclusions or recommendations, at least, don't increase the set point beyond the 800 ppm. That's simply not worth it unless you grow in a vertical farm situation where hardly anything is lost. Dose CO2 effectively, so only dose it preferably with low window openings. Dose in the morning, decrease the CO2 dosing in summer. less CO2 will almost always result in lower yields. But if you're decreasing the CO2 inputs by 70% and you're getting 1 or 2% less product, and also imagine that product that you miss is also during the summer, when generally speaking product prices are a lot slower, it might be worth it to just stop or decrease CO2 by quite a lot. There are some companies like Baymax CO2 Optimizer who also take that into account. That was my talk for today. I'd like
Thank you very much, Stijn, for this brief introduction. Round of applause. We need a few seconds to switch to the next presentation. And I would like to challenge you, Stijn, to think about what happens when we grow with less CO2. Because there is also some literature available that say when you grow with less CO2, it not necessarily gives you a lower yield because the plant are making more stomata at the same time. So I'm encourage you, what's the impact on that?
Yeah.
I didn't saw it on your, but maybe in the panel you can think about it. That was the time to switch to you.
Yep.
Birgit,
here we go.
here you go. Your 8 to 10 minutes starts.
Alrighty, thanks so much. Yeah, thanks for this opportunity actually to be part of this panel discussion about overview of developments in CO2. More specifically, I'll talk a little bit about the balance between production and footprint. But before I get started on what I would like to discuss, just a brief introduction of myself and my organization. So my name is Brigitte Jacobs. I work as a business lead in the unit of energy and material transition at TNO. Now, probably most of you know that TNO is the largest independent research institute, applied research institute in the Netherlands. And in the field of energy and material transition, we basically work on technology developments in renewable energy. Think about solar, wind, and whatnot. And also on decarbonizing technology. I guess you guys have all heard about like hydrogen, electrification, biomass, but also the topic of CO2 capture, transport, and storage are all technologies that can help industry reduce their carbon footprint. So that's TNO in a nutshell. So what I would like to discuss actually in the next 10 minutes, and I'm glad that Stijn already kind of covered the second bullet point, because otherwise I would not be able to squeeze it in. I'm going to talk a little bit about global developments in the CO2 market, so talk about storage and utilization that is really exponentially growing as we speak. Like I said, I will briefly, but most of it has already been discussed, talk about use of CO2 in greenhouses. And yeah, last but not least, I'll elaborate a little bit more about new technologies that can be used at greenhouses to basically assure the CO2 as a source. So with that being said, let me just take you through the landscape of the CCS market. So I already mentioned carbon capture, transport and storage is really exponentially growing in the last couple of years. Especially in Northern America and Europe, I mean specifically driven by policy, I would say. We've seen indeed project pipelines that have grown with like 35% on an annual basis. Today we're at about 41 commercial facilities worldwide. But like I said, indeed, there's way much more in the pipeline. Yeah, so like I said, it's fair to say when it comes to the CCS market, it's most likely that most of the CO2 will actually be stored under the ground, so to say, in order to reduce the CO2 emissions. Now, besides storage, there's also an opportunity of using CO2, and there's already an existing market today. This gives an overview. It's a significant market, and the majority of the CO2 today is really used in fertilizer application as well as enhanced oil recovery. Actually, only a small part is used in like, the food and beverage, but also the yield boosting that we're talking about right now. So today I think this is the major use of utilization of CO2. What is expected for the longer run is also that some of these CO2 molecules are going to be converted into useful molecules to make like fuels or plastics, because obviously we foresee a battle of carbon in the future, and that CO2 molecule might become of even more value. I'll go a little bit more in detail later in my presentation on that one. So what I now would like to do is just have a closer look at the cost of capturing, because it is a technology that comes with a cost. Basically, I'm going to take you through the different steps of the value chain. So the first, the capturing step, and I'm talking predominantly about the post-combustion capture step, whereby the CO2 is captured from the flue gases of stacks. Now, today there are two large commercial scale units. There's one in Boundary Dam in Canada and another one in operation in the US, or at least temporary, it's out of service, but it was in operation there in the order of magnitude between 1 and 2 million tons per year, so to say. So that's a point of reference. In the Netherlands, we actually also have two what we call commercial full-scale capture plants. They are at waste incinerators. So AVR has a capture plant since a number of years, since 2019. You can see, it's a capacity of 0.1 million tons, so 100 kiloton per year. And in addition, also this year at the Twence waste incinerator, also a capture plant was implemented. So as you can see, much smaller size. That's important to stress, because if we look at the cost of carbon capturing, then you can see that this is dependent on a couple of variables. And size, kill size is one of them, as well as quality of flue gases, so to say. So what's the concentration of CO2 in there? Now, typically we expect the cost of carbon capturing today is around like 40 to 80, like I said, depending on this range of what we're dealing with. And yeah, most likely it will decline, it will decrease in the future with new technology implementations, new learnings, both on the CAPEX and the OPEX reduction, to about like, 30 to 50, so to say. So it still remains an important cost, a lot driven obviously by the energy requirements of it. Now that's one step. Then you have the captured CO2, then you need to do something with it. Now this slide actually gives you an overview of the combined cost of transport and storing CO2. So this is a summary of a number of different storage locations, and what you can see here, that your storage costs are dependent on location and way of transport. But on average, we say it's somewhere between 30 to 50 euros per ton that you have to add, so to say. And I think most of the companies, they look at this technology in comparison to ETS prices. So it's a way for them to kind of avoid the cost of ETS. That was it for indeed, like, hey, what's happening in the market of CCS, and like I said, the role that utilization plays. I'm actually really quickly just going to go through the CO2 use in greenhouses, because Stijn did an excellent job in explaining it. What I would like to point out, and I think indeed also Stijn mentioned that, it will be important, because we rely heavily on that OCAP line, or for that matter, it applies to all CO2, to find new sources, to secure supply of CO2 to greenhouses. Especially, and that's what I would like to introduce, like there are two types of CO2 molecules. There are the gray molecules that are basically coming from your fossil fuels. And for example, the Shell one that is supplying the OCAP line is an example of that one. It comes from their refinery process. Hence, Shell also is choosing to actually store this CO2 in the future. What the greenhouses are looking for, and have expressed the ambition, that in the future they will only use green CO2, or neutral CO2. And neutral CO2 indeed could be realized by new technologies like direct air capturing. So I'm just going to talk a little bit about direct air capturing, where basically your CO2 is captured from the air and converted into a pure CO2 stream that can be used in the greenhouses. Now, if we look at the technology landscape, then it's fair to say there are mainly two lines, so to say. There's one based on sorbent technology, which basically is a solid material, and there's another one based on solvent technology, which is a liquid material. And then what you see is, within those two development lines, different technologies are being added continuously, so to say. So this landscape, like I said, it's growing rapidly, but a lot is going on there, and indeed there is a future foreseen for this technology. Last year, TNO did a study on behalf of LTO for the greenhouses, and there, it seems that the best option for the horticulture sector is actually the sorbent route. So I'll just talk a little bit about that one. Because actually for the sorbent technologies, there's one full-scale duck capture unit in the worldwide. You guys may have heard of Climeworks. They've built this capture unit. It's located in Iceland. There are 4 kiloton of CO2. It's the Orca project. 4 kiloton of CO2 is being captured from the air and stored in basalt. So that's counted as negative emission. And actually, indeed, they sell it as voluntarily credit to, at this time, it's more like investors. I think actually one of their customers is like Microsoft, Google, have really for offsetting at €1,000 per ton. So let's take a closer look at the cost. I mean, Stijn also mentioned it. I think it's fair to say today, obviously, the costs are very high for this technology. But let me indeed shed a little bit of light of what to expect from those costs in the future. So I'd like to touch on 2 parameters, because what we've seen is cost is dependent on the development stage. So what you see is indeed from startups and I would say bold claims that say we can do this for less than €100. I mean, you see that typically, and maybe it's optimistic stage of new startups, but that prices are high at that stage. And then indeed, with testing, the prices become more realistic. We believe that that realistic prices are somewhere around the 200 to 500, and actually that is confirmed also when you put it in correlation with deployment size. So with the growing magnitude deployment size of duck, we expect costs to lower. So today we're at the order of magnitude of a few kilotons. Now that's fair, €1,000 per ton. And again, with the growth into gigatons, we expect those costs to decrease to about 200 to 500. Now, just to finish up, so what have I talked about? Basically, the CCS is going to grow exponentially in the next coming year. It's really seen as a technology that helps us reduce our CO2 emission. Cost of capturing between 40 to 80 today. Cost of storage lies between 15 to 30, gives you an idea of what the cost is in the market. Now, utilization will be limited in the future. Majority, especially of the gray CO2, will be stored. DUC is a technology under development, has potential. Current costs are high, but we expect them to decrease to about 200 to 300. I already mentioned, it's important for greenhouses to look at this biogenic or CO2 neutral molecule, I would say. So you might consider being close to energy for waste that has biogenic CO2, or power mass, biomass that has CO2, or indeed install a DUC unit. And as with many energy transition technologies, it's always best to try to reduce your consumption of CO2. So I leave it at that.
Thank you very much, Brigitte, for this inspiring presentation. Before I give the floor to Wouter Kuiper of Cubo, please, Wouter, join me. I think you are also, you want to know who are farmers or greenhouse growers here in the room.
Yes.
Please raise your hand if you are a grower yourself. And
Good. Good.
I think that's good.
Yeah, of course.
Potential public. And from who are you is working already on carbon capturing and have some ideas around it currently? Please raise your hand. A lot to gain, I see. I'm very glad to introduce you to the CEO of Cubo Greenhouses, greenhouse construction company for over how many decades? You will explain yourself.
Almost 80 years. Yeah.
And also the inventor, of course, of the ultra-climate greenhouse with your partners. So a big round of applause for Wouter, and he will explain more about the positive or the negative carbon greenhouse. The floor is yours, Wouter, if you need. There you go.
I don't have a presentation.
You do it out yourself.
Yes, yes.
Great.
So, yes, my name is Wouter Kuiper. And yes, I am proud to say that I'm proud to be CO2 negative. And this comes from somewhere. And I would like to take you on a journey where we come from and where we are now today. So, 50 years ago, you said it already, we were the co-founder of the semi-closed greenhouse, and that we call the Ultra Climate Greenhouse. That was in California together with Casey Howling. And then you start selling these greenhouses, and actually already with the first greenhouses, you figure out that, hey, this is a whole different way of growing, and the growers need support to make the transition from conventional growing, as we call it, to ultra climate growing. So we built up a support team. So we have growers in our company working for our company. We have also scientists working for our company. And then at a certain moment, you feel that there's more possible with the ultra climate greenhouse. There's something behind the horizon, but you cannot see it yet. So we said, okay, we go to some of our customers and we ask, can we use a part of your facility to do some trials and tests? Now, I think you can imagine what the answer was. It was, of course, no. Please don't touch my bread and butter. Understood. So we said, okay, we built our own test facility. We started with that 5 years ago. We are now at our fourth crop cycle. And the first year was learning. We didn't know anything about growing. Now we do. So also our team can talk with you as a grower. But anyhow, with actually 3 goals. One goal was, okay, how can we make growing easier? Because growing is not easy. It's actually an industrial building, and it is complex. And we need to make this easier, so it's scalable, and you grow with low risk, or you invest with lower risk. So, okay, goal number 1, how can we make growing easier, and how can we automate the growing process? Number 2 was, how can we improve our hardware and our software? And number 3 was, how can we grow with less input, and mainly energy and CO2? Okay, year number 2. At a certain moment in our team, week 16, let's shut off the heating and see what happens. And if you have 1,000 square meters of tomatoes, you can do that. That's why it's a test facility. So, okay, I thought, well, let's see what happens. Probably going to be a disaster. And on the contrary, it was not a disaster. We actually had more kilos in the non-heated greenhouse than in the heated greenhouse. Why? So I asked my scientist, I want to have a reason. What is the science behind it? And the science was actually that because we have more air movement in our ultra-climate greenhouse, because it's mechanical ventilation, you can go to higher humidity levels in the air. So before it starts to condense on your crop, and that's where the diseases start. Anyhow, so we grow with about 22 cubes of gas, we can grow tomatoes. And in the Netherlands, the standard, the traditional greenhouse is between 30 and 35. Okay, I'm going a little bit sideways, but I'm coming back to the CO2 in a moment. But that was an important thing. So we said, year number 3, what are we going to do now? Okay, we're going to grow with less energy. Let's just take the ambient CO2, what's in the outside air. Well, that's a bold idea. What will happen? And again, we thought, or I thought, okay, the result will be less kilos. But it would be, I was interested, can we then grow maybe with lower cost? And at the end also a lower cost per kilogram. So we started, and again, the end result was not what I expected. We saw actually the same yields with actually lower CO2 input, or actually no CO2 input. Yeah, the input from the outside air, but we didn't inject anything. Again, how is this possible? This is quite remarkable, and actually a revolution in a way, because we don't need expensive machines to take out CO2 from the air and then inject it again in higher concentrations into the greenhouse, because it's a higher capex, and also you need quite some energy to take the 400 parts per million outside a million to extract that from the air. So anyhow, the reason why this is possible is as follows. This is the science again. And you're more than welcome to visit us at our booth. We are in the Europa Hall. We have a white paper. We have scientists on our booth that can explain you if you want to have a bit of deeper understanding of how it works. And we also have a nice CO2 magazine that explains a little bit on how we do it. But anyhow, now coming back to the clue. So how does it work? Actually, if you give the plant, a plant is actually grown or evaluated in, let's say, hundreds of millions of years. And on Earth, the ppms has been somewhere between 200 ppm and also 1,000 ppm. So the plant actually adapts to the amount of CO2 which is available in the air. The stamina grows to the amount of CO2 which is available in the air. So if there's a lot of CO2 in the air, the stamina grows smaller. If there's not so much CO2 in the air, the stamina grows bigger. And if you do that all the time the same, the plant grows to that amount of CO2. And that actually results in the same amount of kilograms of production. And the nice thing about it is, again, you don't need expensive machines, but you also do not have to burn gas to generate CO2 for your crop. And you also do not have to pay, because that's where we are going to, eventually, especially in the European Union, with rules and regulations of the CRSD, that we have to pay for, if you emit, you have to pay CO2 emissions. And in our case, you do not have to pay CO2 emissions. So you really reduce your CO2 footprint massively. So what's going to happen? Oh yeah, and so at the end the cost price is lower, because you don't have to buy CO2, you do not have to generate the CO2. So at the end of the day, the cost price is lower, and you have a cheaper product to sell, or you earn more. That's eventually what we do. And so again, if you would like to know more than welcome to come to our booth. We have lots to tell you. Thank you very much.
Thank you very much, Wouter. And I think this opens the floor for a very nice discussion. Because when you are here the whole morning, this is, let's say, 45 minutes, you probably have heard an opposite story. At least, I'm not a technician, but I heard a little bit from Stijn that he said, okay, more CO2 gives a higher yield. And Wouter is saying, it's not needed. It's not needed. It's the plant that adapts to the amount of carbon that is in the air. And if it is not in the air, it still grows smoothly. Do I right, guys?
Yep.
But you are the experts. I'm only the moderator of this morning. So, of course, you want to know more. I want to know more about it. So, Stijn, first up to you. I asked this question between already. So, give us a short answer, because we have many questions. So, keep it.
Keep it short. Okay, lots of pressure. I like the idea of it just getting used to the lower concentration of CO2. I know the plants have been developed, indeed, with 200 and 1,000 parts per million, but that happened in millions of years, and not necessarily one cultivation cycle of, let's say, 30 to 40 weeks. So I'm just, and that's maybe a learning opportunity for me as well, is to, well, I'd like to talk to your scientist about it.
Yeah.
Because if that's true, what you're saying, that it is better to just keep a same level of, let's say, between 400 and 500 ppm, then we would not be losing lots of CO2 in the summer. And that would also mean that we would have to have lower concentrations during the winter, when it's used very efficiently.
Yeah.
And it's something that we have not put in a trial before, so I cannot say which one's better, but it is very exciting.
Wouter, do you want to react on
Yeah, now
what is the winter?
Yeah, kijk, and it's also what you said, what you stated in your presentation. The amount of emission you have is massive, because 90%, and then we use the same numbers because we use the same science. So 90% of the CO2 actually emits, which is about 300 to 400 tons of CO2 per hectare per year. We did it with minus 60 with the same yield. But yeah, it's. I would say, start your trial or elaborate with our scientists. More than welcome. Yeah.
My question to Birgit is, what is your takeaway message for the farmer that is maybe not located in the Netherlands? Some of your slides were more oriented to the Dutch.
Yeah.
What do you recommend as a first step for a grower outside in the US or the UE to do today to make,
So obviously I already made the distinction in CO2 molecules that even though, from a scientific point of view, they look identical, but there's a difference between a gray CO2 molecule and a green CO2 molecule or a carbon neutral CO2 molecule. So forget about the gray molecule. I think indeed their best solution is make sure that they never get released to the atmosphere again. When it comes to green, as I pointed out, the technology indeed of capturing it from biogenic sources obviously is an easy one. I already indeed said, if there are opportunities of having indeed your greenhouse close to a power operation that is based on biomass or energy for waste that has about 50% of their CO2 being green, great, work together and indeed work with their CO2, so to say. And if that's not the case, indeed, really consider CO2 from the air, as a way of really securing the supply of CO2 in the future.
Then I would like to make the combination between the two of you, Wouter and Birgit, is on, as you said, it is something about bio-waste, using the gas from bio-waste. How far is into practice to have a farm, a greenhouse of 10 hectares or maybe 20 hectares that is heated by the gas that's coming out, by the carbon, but as well as the fertilizers? Because when you make a greenhouse negative, what about the fertilizer? Is that coming from the waste stream as well? And are we going then exactly to the direction that it is negative as much as possible? And how far is it to the future? We have a few minutes. Can you highlight the horizon for today?
There are a lot of variables possible. So it depends a bit what is your situation, what country are you, what rules and regulations are there, and what sources are there available. So that's very depending on those factors. But for example, we are building projects in Scandinavia together with WARM. They actually buy the waste streams from industry. We build the greenhouse and use the heat from that. So actually you're already energy neutral, and the CO2 is from the air. So you're actually already growing food with a zero footprint. So that can be done, but there's multiple ways. You can, and there's also an existing industry. Do we have to completely renew it? I think we do. Yeah, that's my job. I'm a greenhouse builder. But of course, there will be also other possibilities to reduce your CO2. But negative, then you have to go to an ultra-clean.
But are you also using then the fertilizer part out of the waste stream already, or is that too far? Because that's another big emitter of.
You mean the irrigation? Because CO2 is also fertilizer. That's you can't get that out of the bio waste. So that has to come from different streams. But that's also possible you have natural fertilizers, and it's coming as well.
Yeah, and I know that also fertilizing manufacturing is looking at decarbonizing their processes. And for example, both hydrogen and electrification are high on their radar, that indeed they could also claim making CO2 neutral fertilization streams, so to say. But
Stijn. your last sentence. We have just 4 minutes left. What is your takeaway or your message? How they can continue with lowering the footprint? And what can you contribute as Delphi on this?
Good question. I speak to a lot of growers, and growers have had many experience doing the things that they have always done a certain way, which has always resulted in very high yields. The Netherlands is one of the top countries to produce fresh vegetables, fruits, ornamental crops for a reason. Currently there's a challenge to do it fossil-free, and we sometimes have to let go of what we have done in the past, of what we think was right, based on the science, based on new insights. So the discussions that I also have with growers is, Stijn, I need X amount of kilograms of CO2 from an external source, which is the best? And then I always say, take a step back. Right now you need that much carbon dioxide because you just throw it out of the window, but try and limit the CO2 that you lose, for example. And the same is true for water, the same is true for energy.
So we're coming to a direction that we say yield optimization is maybe not the goal for the near future, but optimization of the footprint related to the yield.
I also talk a lot about energy efficiency, and we always stick to the trias energetica, or like the triangle of saving energy, and it always starts with save as much energy, reduce the inputs as much as you can. Before looking at direct air capture, before looking at any other source, try and reduce the inputs.
Yeah, I totally agree. It's about cost price at the end of the day. Kijk, the retail is not really open to say, hey, I'm willing to pay more for your product, even if you have a lower footprint. Or that's, I think, the reality. Yeah. So it's also about the cost price. How do you reduce the cost price as well? And there's numerous possibilities. Okay. So that's the good news.
Yeah.
That's still the bright side of CO2.
Yeah. It's the bright side of CO2.
Yes.
Yeah. Okay. I'm looking around and to see, we are going to round up this very nice discussion on what will be the future on carbon. How are we going to capture carbon? Or do we don't need to capture carbon and use the outside air carbon and to grow plants? What is a kind of paradigm shift from the Delphi guys. So you have to squeeze up something like that. But I know you are strong collaborators within the industry to learn from it. I'm looking around. If you have any question, please raise your hand. Maybe we can pick one or two. We have 1-2 minutes left. And if not, if you don't have a question yet, I'm sure that the experts are...
we will hang around. Eh?
You will hang around here for a few minutes. Yeah. They don't run back to the booth. And you can catch them and ask your question in a more private mode. So if not, I really would like to thank you very much. I would like to thank Wouter. Thank you very much for being here today with us. Thank you, Stijn. Thank you, Birgit, for all your insights and valuable knowledge here on stage. Thank you very much. I wish you a very nice morning here, and see you later.
Nou, hey.
Ja.
Bedankt.
Was leuk.
Was
leuk.
Wel even langs,
ja, goed, die wilde ik sowieso geven, maar meer dan welkom.
Ja,
mevrouw Manders, dus ik ben er ook